Today we will continue with constant and non-constant acceleration. During the last lecture, we have seen displacement and the relation between velocity and displacement, and also the relation between acceleration and velocity, acceleration and displacement. We have learned instantaneous velocity, instantaneous acceleration. We have also learned average velocity and average acceleration. We have also seen the difference between velocity and speed. So today we will go into detail with the acceleration, and we will discuss two situations. The first one is constant acceleration, and at the end of the lecture we will discuss the non-constant acceleration, how acceleration affects our real life. Here you see a test pilot. These experiments were carried out in the 1940s and 1950s by the United States Air Force. So this guy, test pilot, riding a rocket sled, in Turkish rocket kıza, could withstand acceleration as great as 440 meters per square second. Huge acceleration if you compare with the gravity. So the first three photos here, this photo, this one, and also this one, show Air Force physician John Stepp speeding up from rest. Now velocity is 0. And here in that picture, after 5 seconds, the velocity is 188 meters per second. So in terms of kilometer per hour, you can see here 678 kilometer per hour. Huge velocity within 5 seconds, okay? So then there is a huge acceleration. So they investigated the effects of this high accelerations on the metabolism of this test pilot in the United States. And here the pictures 4, 5, and 6, last three pictures, show even greater magnitude of acceleration as the rocket sled braked to a halt. So here within these three pictures, we have acceleration from rest to the 188 meters per second. And here, during the last three pictures, the pilot is stopped, okay? And then we have negative acceleration. So you see the effect of the acceleration on the pilot. So this is also valid for the fighting jet pilots. Here we have example from Turkey. This is pilot within the F-16 solo fighting jet. So during this type of movements, the plane is accelerated a lot, okay? And then this pilot feels very high accelerations. Here you see another example. This is the Falcon Heavy from SpaceX. So you see it starts again from the rest and it reaches to the very high velocities within a very, very short time. And then there is very high acceleration. So these three examples show us how acceleration is important. It can be constant, it can be non-constant, it can also be 0. So we'll discuss all these things within this lecture. So first of all, let me continue with the constant acceleration, motion with constant acceleration. Here we have an x-axis. This is the origin, and this is the positive x direction. Here again, origin, positive x direction, origin, positive x direction, origin, positive x direction, origin, positive x direction. So here we have the time is 0. Here we have the time is delta t. Here the time is 2 delta t, 3 delta t, 4 delta t. So we have same time intervals between these different movements. So what do you see here? The particle is moving along the positive x direction with constant x acceleration, okay? So since the direction of the acceleration and direction of the velocity are same, as we have discussed during the last lecture, this particle is speeding up along the positive x direction, but the acceleration is constant, okay? So here, since we have constant acceleration, after certain time, after delta t, the velocity will be increased, okay? And this is the x, the displacement during delta t. And during same delta t, after this one, the velocity is increased again. But what do you see here? The velocity changes by equal amounts in equal time intervals. So within each delta t, the velocity changes by equal amounts in equal time intervals. So here we have certain velocity, here we have more velocity, here we have more velocity, here we have more velocity, and we have the highest velocity here, but the acceleration is constant, okay? So due to this acceleration, our velocity changes. Velocity increases here in that picture, okay? And within the same time intervals, the displacement is different. This was the initial position of the particle, and now after delta t time, this is the second position of the particle. After another delta t time, this is the third position of the particle, this is the fourth position of the particle, and this is the fifth position of the particle. So what do you see here? We have different displacement in the same time interval due to the acceleration. So we will go into detail about this behavior with the constant acceleration. Now let me show you acceleration versus time graph. Acceleration is constant, it has certain magnitude, and it does not change by time. So what do you see here? There is an area. This was the time is 0, and this is the time is t, and acceleration is constant for all time values. So what is the area here? Let me remind you the formula from the last lecture. What was the average x acceleration? Average x acceleration is given by delta vx over delta t, right? We have done it during the last lecture. What is the meaning of that? X is the final velocity of the particle here when the time is t. V0x is the initial velocity of the particle when the time is 0. And here we have delta t. Since the initial time is 0, I can write here just t. And if I use that relation here, then if you multiply this one with this one, then A average x times t is equal to Vx minus V0x. You can get this expression, okay? So what is A average x? Average acceleration. So since acceleration is constant here, it does not change. So instead of average x acceleration, I can use instantaneous acceleration. For each time, acceleration is constant. So then this is equal to ax times t. So what we have here, ax times t. This is the ax, this is the t. And the area under this curve, ax times t, and we have already calculated this one. This is equal to Vx, final velocity along the x-axis, and initial velocity. Is it clear?
Yes.
Okay,
Yes.
thank you. Now let me continue with the velocity versus time graph. And what do you see here? This is the origin, and time is 0 here. Let me write like this. When the time is 0, the velocity is given by V0x. And when the time is t here, the velocity is given with Vx, okay? So during the previous transparency, we have calculated this one. So Vx minus V0x gives us Ax times t, this one. And here we have V0x, okay, and this is the Vx. So we have this relation. So what is the area under this curve? Now I will show you the area under this curve. So this area. This is the area which is given by total displacement, okay? This is the initial position, and this is the final position, let's say. This is the x0, this is the x, and total displacement, delta x, is given by x minus x0, right? And the area under this Vxt graph gives us the total displacement. So now we will discuss all these things in detail. Here we have 4 equations of motion with constant acceleration. By using this equation, this one, and also this one, you can answer any question with the constant acceleration. For this reason, you have to keep these equations in your mind, okay? These are very important, not only for chapter 2 of university physics, also for chapter 3, chapter 4, chapter 5. For each forthcoming chapter, these equations will be very useful if acceleration is constant. These equations are only valid if the acceleration is constant, okay? Now I will try to get these 4 equations by doing some calculations. Now let's try to get this one, 2.8, first one. Actually, we have done it in the previous transparency, but let me show you here again. So when the x acceleration is constant, the average x acceleration for any time interval is the same as ax. So instead of average x acceleration, we use instantaneous acceleration because acceleration does not change by time, okay? It is always ax. So instead of average x acceleration, as I have discussed during the previous transparencies, I just use ax, acceleration along the x-axis. So you know from the first lecture of chapter 1, this is given by delta v, final velocity minus initial velocity, over delta t, final time minus initial time. So you know this one. So let's consider that t1 is 0. So you start from when the time is 0, and then t2 is t, okay? And final velocity is vx, and initial velocity is v0x, velocity when the time is 0. Instead of t2, just use t here. Instead of t1, just use 0 here. So then finally you can get this expression. This is the final velocity vx, velocity along the x-axis, and which is equal to initial velocity of the particle when the time is 0 plus acceleration of the particle times time. So this is the equation 2.8 here, okay? Never forget this one. Now let me continue with the second equation. How to get this equation? In order to get this equation, we will just use the average x velocity. So remember the average x velocity formula from the last lecture. Let's consider that t1 is 0 and t2 is t, and this is x, this is x0 when the time is 0, okay? Then this can be written in this form, x minus x0 over time. Then the displacement can be written in this form, total displacement delta x is given by with this expression. Now we have this relation. So now let me come back here. Here we have velocity. Here we have increased velocity. Here we have more increased velocity. So velocity increases, but velocity changes by equal amounts. Okay, so let's consider that at the beginning it is 1 meter per second, then here 2 meter per second, 3 meter per second. So what is the delta V here? 1 meter per second. Here, what is the delta V? The change in the velocity, 1 meter per second. Here, let's consider 4 meter per second. And then the delta V again is given by 1 meter per second. So x velocity changes by equal amounts, okay, in the time intervals. So what is the meaning of that? Let's also put here 5. This also have same amount of change. So now I would like to calculate V average x. So how to get the average of these numbers in mathematics? 1 plus 2 plus 3 plus 4 plus 5 divided by 5. Then you can get the average, right? Instead of doing that, you can also do like this. Initial velocity plus final velocity divided by 2. Then this will also give you average value of the velocity. Here we are doing this. Initial velocity plus final velocity divided by 2. This is only valid for this condition. This is just comes from the mathematics. Is it clear for you? Do you have any question here? Here we have x velocity, you see, within this equation. X velocity is equal to v0x plus axt, right? And just use it here, okay? Instead of vx, we have v0x plus axt. Then finally we have this relation, v0x plus 1/2 axt. Here we have one v0x, another v0x. There will be 2 v0x. If you divide by 2, then I will have here 1 v0x plus 1/2 axt, because I multiply this one with 1/2. And what we have here, this is the v average x, and it is equal to v0x plus 1/2 ax. Here we have another v average x, which is given by x minus x0 over t. It is equal to x minus x0 over t, this one. I have just taken this one and put it there because both of them are equal to v average x. So then here on the left side, I have v0x plus 1/2 axt, and on the right side, x minus x0 over t. So just multiply this term with t, and finally we will get this expression. This is the final position of the particle with constant acceleration, initial position of the particle when the time is 0, and x velocity of the particle when the time is 0. This is the time, and this is the constant acceleration. This is the square of the time. So now we have another equation. The final position of the particle is equal to initial position plus this term plus this term. So what are the units? This is the meter. This is also meter. What is velocity? Meter per second. Here we have second. Again, the unit of this term is also meter. And here we have a meter per square second. And here we have square of second again. So the unit of this term is also meter. So all these things are showing us displacement of the particle with different meanings. So now let me explain. This x0 here, it is the initial position of the particle when the time is 0, this one. And this is the displacement if the x velocity remained equal to its initial value. So let's consider that there is a car. It is moving with constant velocity for certain time, okay? There is no acceleration, and then you have this displacement. This is the initial position. And plus, after a certain time, the car started to accelerate. Then you have acceleration here. So this is an additional displacement caused by the change in x velocity. If you have acceleration, it means that velocity is not constant anymore. So you have an additional displacement due to the constant acceleration or changing velocity. Do you have any question related to this equation? Is it clear for you?
Yes, clear.
Okay. Now let me show you here. We have a dragster, a race car, moves in positive x direction. Let's say this is the origin, this is the positive x direction, and this is the initial position of the car, x0. This is the initial velocity of the car when the time is 0, v0x, and this is the final position of the car, x, and this is the final velocity of the car. Final velocity is given by initial velocity plus ax times t. So here, during time interval t, the x velocity changes by this ax times t. So this is delta v, change in the x velocity of the car, so which we have done in the first equation for the motion with constant acceleration. Here we have another graph. This is the x-axis again, and this is the time axis. This is the time is 0, this is the time is t. And here the position is x0, and here the position is x. So what we know, xt graphs gives us velocity, right? We have discussed during the last lecture. Let me remind you the formula here again. Average x velocity is equal to delta x over delta t. This is the delta x, right? This is the delta t. So the slope of this one will give us this average x velocity. Here I am looking for the instantaneous velocity. When the time is t, slope is given by vx. And here I'm looking for the instantaneous velocity. When the time is 0, the slope is v0x. Okay, so we have parabola for the constant x acceleration. Xt graph is a parabola. Do you have any question here? Then let me continue with the xt and vxt graph. Here we have xt graph and the same graph here with more details and comparison with 0 acceleration. And here we have vx and time graph, okay, for the constant acceleration. So for the constant acceleration, this is the 0 time, this is the time t, let's say, and here this is the 0 position, x0 when the time is 0, and let's say this is the final position, okay? So what do you see here? X here is given with this expression, which we have calculated just a few minutes ago. X is given by x0 here, initial position, plus v0xt plus 1/2 axt square. So it is a parabola, okay? But if ax is 0, so let's consider that there is no acceleration. Ax is 0. Then this term, the third term here within this x will be 0, and then we will have this one, x0 plus v0 x times t. So the curve will be like this then. This is the graph for this condition when the ax is 0. So here there is no acceleration. So acceleration produces such behavior in the xt graph. Now let me continue with the Vx graph. Here we have Vx velocity, and let's say this is the final Vx, and this is the initial velocity when the time is 0, and this is the final time t, and this is the 0. So what do you see here? Vx is given by v0x plus axt. So if we have constant acceleration, okay? So if the acceleration is 0, let's consider that. If ax is 0, so it means that there is no acceleration. So this term then will be cancelled, and Vx, final x, will be v0x. Then you will have this type of behavior. So by time, your velocity will not change. Okay, initial velocity and final velocity are same if the acceleration is 0. But if acceleration is different from 0, let me delete this one, then we have this type of change in the x velocity. Velocity increases by time if the acceleration is constant and different from 0. Do you have any question? Then let me continue. So in order to solve this equation and also this equation, you have to know the time, right? But let's consider that within the question, time is not given and you don't know the time. What to do? Then you can use this equation, which does not include the time. Okay, there is no time here. So if you don't know the time, you can use this equation for the motion with constant acceleration. So how to get this equation? This was the equation 2.8, or you know this equation like this. Vx, take this guy to the right side. V0x plus axt, okay? And here we have t. Just take this t. You can write it like this. If you take t from this equation, equation 2.8, t will be vx minus v0x over ax. So this is the t. Then just use this t in equation 2.12. What was 2.12? 2.12 is this one. Here we have t and t square. Just use t and t square here. Let me write equation 12. X, x0 plus v0 x times t plus 1/2 ax t square. This was the equation 2.12, right? So instead of t here, instead of t square here, just use this t. Okay? Instead of t here, just use vx minus v0x over ax. So if you solve this one, finally you will get this equation. Square of vx, final velocity, square of v0x, initial velocity when the time is 0, plus 2ax, constant acceleration of the particle, times final position minus initial position when the time is 0. And in some questions, it is also given as delta x, displacement. Okay, so now we have equation 2.13 and it does not contain any time. So t is missing here. If the time is not given within the question, this equation is very, very useful for the constant acceleration. Okay, now we have also calculated this one. Now let's have a look, the final one. So what do you see here? Here we have t, but what is missing here? The acceleration is missing here. So within these three equations, acceleration is given in the question. Okay, let's consider that acceleration is not given in the question. So what to do? Then you can use this equation. So acceleration is not given here. Then this equation will be very, very useful for you. Now let me try to get this equation. It is very simple. So what to do? Equation 2.9 and equation 2.10. What was 2.9? Equation 2.9. Equation 2.9, this one. X minus x0 over t. And equation 2.10, 1/2 v0x plus vx. Let me delete this one. You can see better. I will use these two equations. Okay. So what do you see? Average x velocity, average x velocity. So they are equal to each other. So just use them. So what was equation 2.9? V average x was equal to x minus x0 over t, right? Let's have a look. And then this one, average x velocity is equal to 1/2 v0x plus vx. So both of them are same, and just take them, x minus x0 over 2. This one I have used, and then take this one, put to the right side, 1/2 v0x plus vx. Sorry, here we don't have 2, we have t. Here we have t. Okay, so just multiply this side with t and multiply this side with t. Then finally we will get this expression. Final position of the particle with constant acceleration, initial position of the particle when the time is 0. They are coming from this side. And t will go to the right side. Here we have time. This is the initial velocity when the time is 0. This is the final velocity when the time is t. So we have this type of relation. What is the importance of this equation? Here we don't have acceleration. It is very, very helpful. So now we have all of the equations for the motion with constant acceleration. So as I told you at the beginning, these equations are very important and very useful. So you have to use these equations for the forthcoming chapters also if the acceleration is constant. And I would like to remind you here that if the acceleration is not constant, you cannot use these equations. You cannot use these equations if the acceleration is not constant. These are only valid for constant acceleration. Okay, do you have any question here? Okay, I think during the last lecture, Dilek asked me how to study, how to solve the problems at the end of the chapters. So, for example, for this chapter, you can see the problem-solving strategy within the book. So, for each chapter, more or less for each part of the lecture, each part of the topic within the chapters, you can find this type of problem-solving strategies within the book, okay? So here there are many steps, many important points. So if you are dealing with motion with constant acceleration, if you have a question related to the constant acceleration, so this explains how to solve this type of questions. So please carefully read this problem solving strategies. It will be very helpful for you in order to solve the problems at the end of the chapter. Okay, now let me give you one example and then I will have a break. A motorcyclist heading east. This is the east, okay? This is the origin. This is the positive x direction and it is chosen as east. Heading east through a small town, accelerates with a constant 4 meters per square second after he leaves the city limits. Here, there is the city limit, şehir sınırı, Kocaeli'ye hoş geldiniz gibi. Okay, at time t is equal to 0, he is 5 meters east of the city limits signpost. Here, when the time is 0, the distance between the motorcyclist and the city limit sign is 5 meters. And its velocity is 15 meters per second. Find his position and velocity when the time is 2 seconds. So here, the time is 2 seconds. What is the position of the motorcyclist and what is the velocity of the motorcyclist just after 2 seconds? So here we have acceleration of the motorcyclist, 4 meters per square second. So now identify and set up. The x acceleration is constant, which is given. So we can use equations for the motion with constant acceleration. So we take the signpost as the origin. So this is the origin. X is 0. And then we choose the positive axis from origin to the east. This is the positive direction. The known variables are the initial position. Initial position is given and initial velocity is given and also acceleration is given. Okay, these are the known variables and unknown target variables. This is the position when the time is 2 seconds and velocity when the time is 2 seconds. These are the unknown target variables. And in part B, unknown target variable is what is the x, what is the position when the velocity is 25 meters per second. So then which equation you have to use from these equations? So which one is useful for you? When you are solving problems related to that chapter, motion with constant acceleration, always keep these equations somewhere on your table, okay? Don't forget, this is very helpful. So I can use this equation for the position. Final position is equal to initial position plus v0x times t plus 1/2 ax t square. So initial position is 5 meters. It is given within the question, 5 meters initial position. Initial velocity is given, acceleration is given. So initial position, velocity, and time is 2 seconds. We are looking for the position when the time is 2 seconds, and acceleration is given, which is constant, and time is 2 seconds. Put them here. So when the time is 2 seconds, the position of the motorcyclist is 43 meters. Then what is the velocity when the time is 2 seconds? You can use this equation. This is 2.8. Vx is equal to v0x plus ax times t. What is initial velocity? 15 meters per second. It is given. And then acceleration is given 4 meters per square second. And time is given 2 seconds. Then the Vx is 23 meters per second when the time is 2 seconds. Okay, so just by using the equations here, you can easily answer the question. So now let's have a look at the second part of the question. Where is he when his speed is 15 meters per second? So the time is not given here. Okay, I don't know the time. So then I can use this equation. Equation 2.13, Vx square of final velocity is equal to square of initial velocity plus to a x minus x0. So x0 is known, final position is asked, where is he, okay? This x is unknown, and acceleration is constant, it is given. Initial velocity is given, and the speed is given, final velocity is given, initial velocity is given. So use them here, and then finally you can get x, 55 meter, okay? So when the position is 55 meter, it has velocity with 25 meter per second, okay? You can also use other equations and you can get the same result, but this is the fastest method by using this timeless equation of motion for the constant acceleration. Do we have any question here? Okay, then let me give you a short break and then we will continue with the free falling bodies. In the first part, we have discussed motion with constant acceleration, and here we will learn free falling bodies, and this is very nice example of the motion with constant acceleration, more or less constant acceleration. So within the calculations, we will consider that free fall is a motion with constant acceleration. So what is the free fall? Free fall is the motion of an object under the influence of only gravity. So here you see a ball, okay, and you release this ball from the rest and then it falls. So you have a very nice photography machine, for example, and you take pictures for every nanosecond or millisecond, let's say, okay, and then you record the position of the ball for each time interval. So here, let's say after 1 millisecond, after another 1 millisecond, after another 1 millisecond, after another 1 millisecond. So at the equal time intervals, you take the pictures. So what do you see here? Displacement after, let's say 1 millisecond, you have this displacement. After another 1 millisecond, you have this displacement. And here, again here, within 1 millisecond, we have more displacement compared to this displacement. So the mechanism is same as I have discussed in the motion with constant acceleration. Remember this figure, this was the x-axis, positive x direction, this is the 0 initial position, and here we have certain velocity and we have constant acceleration. So for equal time intervals, you record the position of the particle x. So what do you see here? After delta t, this is the position. After another delta t, this is the position. After another delta t, this is the position. So displacement for each time interval is different. So displacement is increasing by time, and velocity also increases with equal amounts if the acceleration is constant. So this free fall is very nice example of this type of motion. Okay, so now let me go into detail. Maybe I should tell you here that what about the acceleration here? What is the source of acceleration? The source of acceleration in free fall is gravity. Okay, but what about gravity? Is it constant or not? So from the high school years, you know that gravity is given by this equation, 9.8 meter per square second, right? This G. Actually, we consider that it is constant if, in addition, the distance of the fall is small compared with the radius of the Earth. So just consider the radius of the Earth and a particle is coming from the space, then the distance of the fall is large, okay, huge compared with the radius of the Earth. But now within this lecture, within this course, we will deal with falls for example, 5 meters from ground or 5 kilometers from ground. So we are dealing with small distances, okay? And then during the free fall, we will also ignore all other effects due to the Earth's rotation and then resistance of the air, okay? We will ignore all these other additional effects, and we will consider that only we have influence of gravity, okay? So this is the free fall. Now, let me give you some information about the G. This is the acceleration. This is the magnitude of the acceleration due to the gravity. So if you are talking about acceleration, it must be vector, right? Indeed, the G is also vector, but here I show you the magnitude of this vector. And in your calculations, you have to be very careful with the direction of the G. I have one example for this situation. So G is given by 9.8, approximate value near the Earth's surface. Okay? This is important. And on the Moon's surface, the G is equal to 1.6 meter per square second, much smaller than the G on the Earth's surface. And near the surface of the Sun, G is much higher than the G on the surface of the Earth. It is equal to 270 meters per square second. So these are the G values for Moon, for Sun, and for Earth. So we consider that in our calculations, usually in the questions or problems in this chapter or in the forthcoming chapter of the university physics, G will generally be taken as constant number, okay? And here, let me remind you this caution from the book. If you are using the magnitude of the G, you will get always a positive number, okay? Remember the vectors, magnitude is always positive. But in vectors, we have direction, positive direction, negative direction. So since this is also acceleration and this is also a vector, it will have also negative and positive sign, okay? So if you take the positive direction to the upward, as we do in most situations involving free fall, the acceleration is negative, downward. Now, maybe let me draw here and you can better understand. Let's consider that here we have a building. One man or lady is staying here and living something from this position, okay? So what is the G here? What is the sign of the G here? Acceleration. It depends on your choice. If you choose, for example, positive Y direction here and the origin here, then G is due to the gravity of the Earth, okay? So the sign of G here will be minus G, since the direction of the acceleration due to the gravity from positive to the negative side. Okay, then let me continue. As I have discussed in the whiteboard, if you take the positive direction to be upward, the acceleration is negative, downward, and equal to minus G, okay? Be careful with the sign of G or you will have trouble with free fall problems. This is the caution from the book. So here you will see within the example. Since acceleration due to the gravity is constant in the free fall problems, you can use the equations for the motion with constant acceleration. So all these equations which we have discussed are valid for the free fall. What do you have here? AX. Instead of AX, you will use G, acceleration due to the gravity. Okay, here you have AX. Instead of AX, you will use G. If you choose the axis Y, then this will be VY. v0y, gt, like this, okay? Let me show you, for example, this one. Vy, final position along the y-axis, v0y plus gt. Sign of the g is very important, positive or negative. It depends on your choice for the coordinate axis. So look at this one. You can also use this equation for the free fall. Now, instead of xy, y0 plus gt square. Instead of acceleration, I use g. This is constant. And here vy square, v0y square plus 2g y minus y0. Here, instead of x, I use y minus y0, 1/2 v0y plus vyt. So what do you see here? Since the g, acceleration due to the gravity in free fall problems, is constant, okay? It has constant value here, which is given by 9.8 meter per square second. You can use all these equations which we have calculated in the previous part by replacing the x with y and replacing ax with g. Is it clear?
Yes.
Okay, thank you. Now let me continue with the example. Here we have Leaning Tower of Pisa, and €1 coin is dropped from the Leaning Tower of Pisa and falls freely from the rest. So you leave the coin free from this position and it goes down. What are its position and velocity after 1 second, after 2 seconds, after 3 seconds? So free fall or falls freely means falls with constant acceleration due to the gravity. So we can use the constant acceleration equations, which I have shown you in the previous transparency. So now we have motion diagram. Motion diagram is very important. So you just read the question and then draw a motion diagram. Then you can easily solve your question. So this is a motion diagram. What do you see here? This is the ground. This is the positive y direction. I have chosen this direction, positive y. And where is the origin? I can choose this ground as origin, or I can choose this first condition as origin. And within this question, origin is chosen as the initial position of the coin, okay? This is the origin. But as I told you, you can also put origin here, but then you must be very careful with your calculations. Depending on your coordinate axis choice, your solution will be different, but the result must be the same, okay? So now, what was the question? What are its position and velocity after 1 second, 2 seconds, 3 seconds? So this is the initial position of the coin. Initial velocity when the time is zero is zero. Initial velocity is zero because we leave the coin from the rest. Durgun halde bıraktık, hiç hızı yoktu. And then the time zero is zero and the initial position y0. Initial position is also zero, okay, because I have chosen this is the origin. And after 1 second, after 2 seconds, and after 3 seconds, what is the velocity v1y? What is the position y1? What is the velocity y2y? What is the position y2? What is the velocity 3y? what is the position y3, okay? So, and what about the gravity? Why this particle is moving in this direction from the rest to the ground? Because there is an acceleration due to the gravity, and this is given by minus g, because it is along the negative y direction, okay? Since I have chosen that this is positive y, then now acceleration is given by negative g, because the direction of the acceleration due to the gravity is along the negative y direction. And in the calculations, you have to use minus 9.8 meter per square second. Did you understand the question and the setup? Now we have identified, and then we set up the problem. So which equations can help me? Vy is asked for certain time, and position is asked for certain time. Then I can use these two equations to give the answer of this question. Now I'm going back. So I will use this equation. Y is equal to y0 plus v0y times t plus 1/2 ayt square. So instead of y0, look at the motion diagram here. Y0, let me show you with the pointer. Y0 is 0 because I have chosen the origin here. Y0 is 0. Put 0 here instead of y0. What is v0y, initial velocity? It is also 0 because the particle starts to have free fall motion from the rest. So v0y is 0. And what is the ay? Ay is given here with minus g, since it is along the negative y direction. Then put here negative g and put time here. For 1 second, you can calculate the position. For the 2 seconds, you can calculate the position. For the 3 seconds, you can calculate the position by using this equation for the constant acceleration. And then what about the velocities for different times? Again, you can use this relation. First equation for the motion with the constant acceleration, Vy is equal to v0y plus ay times t. This is 0 because initial velocity is 0. Then instead of ay, again, I have chosen minus g, okay? And then I have minus 9.8 meter per square times t. So instead of time, just use 1 second, 2 seconds, and 3 seconds within this equation. Then you can calculate velocity of the coin for different times. So these are calculated. What do you see here? Y we have here for the 1 second minus 4.9 meter, and velocity is minus 9.8 meter per second. And for the 2 seconds, we have minus 20 meter for the y and minus 20 meter per second for the velocity. And for the last one, again, I have minus numbers. What is the meaning for the minus y minus velocity? What is the meaning for the minus position? What is the meaning for the minus velocity? This is the origin, and this is the positive y direction. This is the negative y direction. Since the particle is accelerated along the negative y direction, in each case, velocity must be negative, okay? There we have found negative velocities for each times. So what about the position? Look at the position calculations. For each case, position is also negative number. Here, what was the first one? The first one is minus 4.9 meter. The second one is minus 20 meter. The last one is minus 44 meter. So because this is the positive y direction, this is the negative y direction, and the particle is moving along the negative y direction. For this reason, we have positions with negative numbers. Do you have any question here? Is it clear for you? Okay, now I have another example. This is very important. Listen carefully, and then if you don't understand, please let me know. Here we have up and down motion in free fall. So let's consider that again, this is a tall building, okay? This is the building and this is the roof of the building. These are the roof railing. You throw a ball vertically upward from the roof of a tall building. You are staying here and then you throw a ball in this direction, okay, upward. The ball leaves your hand at a point even with the roof railing with an upward speed of 15 meters per second. So when you throw the ball, it has initial velocity, okay? You provide this velocity, 15 meters per second. And then on its way back down, it just misses the railing. So first of all, you throw the ball and then it stops somewhere here and it goes back. The ball actually moves straight up and then straight down. This type of motion here in the motion diagram is just shown for the clarity. Okay, on its way back down, it just misses the railing. Find the ball's position and velocity 1 second and 4 seconds after leaving your hand. Position and velocity are asked, and then find the ball's velocity when it is 5 meters above the railing. Again, velocity is asked, and then the maximum height reached. So this was the initial position of the ball, and you throw it in upward direction, and then this is the maximum height the ball can reach. So the question, what is the maximum height? And then the last question, find the ball's acceleration when it is at its maximum height. So the last question asks, what is the acceleration here when the ball reaches to its maximum height? Who can answer this question? Let's start with answering this question. Okay, very nice. The acceleration is constant. We consider that only G influences the motion here, okay? So, and G is always constant. Gravity is constant. So the ball's acceleration is also constant here for any point, okay? So you can easily answer the last question. So now let's continue with the other questions. In the first transparency, I have explained what is the free fall. Let me go back. We have defined free fall here. Free fall is the motion of an object under the influence of only gravity. So here, what about this motion? This motion from the roof to the positive y direction, let's say. What about this motion? This is also free fall, okay? Maybe you think that only this motion is free fall. No, it is not correct. This motion is also free fall because we are talking about the influence of only gravity also during this motion, okay? For this reason, it is also free fall. Okay, now let's draw the motion diagram. This is the ground, okay? But I choose positive y direction here, upward, and then negative y direction, downward. And I choose that the roof level is 0, origin, where y is 0, okay? And what is the question? What is the velocity when the time is 1 second? And what is the time when the velocity is 0 at the maximum height? What is the maximum height Okay, y is asked. And what is the time when the y is 5 meter? What is the velocity when the y is 5 meter? These are the known and unknown quantities within the question. Okay, then let me continue. So in order to find the position, there are many positions asked within the question. Here we have equation for the motion with constant acceleration, which we have done in the previous transparencies. Y is equal to y0 plus v0y times t plus 1/2 ay times t square. So instead of ay, instead of acceleration, we will use minus g. Why minus g? Because we have chosen positive y direction here upward, and then since the gravity is along the negative y direction, we have to use minus g because gravity is the acceleration and it is a vector. It has direction, okay? So in order to show the negative y direction, we have to put minus here in front of g. So now let's have a look. What is the initial position? Initial position of the ball is 0 because I have chosen this initial position as origin. Positive numbers of the position and then negative numbers of the position. Okay, initial position is 0. Initial velocity is given within the question, and this is the g, minus g. And there are also questions related to the velocity along the positive y direction and along the negative y direction. In order to calculate the velocities, again, you can use the first equation of motion for constant acceleration. Vy is equal to Vy0 plus Ay times t. Instead of Ay, again, we use minus g because we have chosen the positive y direction upward, and the g is along the negative y direction. Then Vy is given by 15 meter per second plus minus 9.8 meter per square second times t. So then within the question, 1 second, 4 second, okay, all these things are given. Just put here 1 second, just put here 4 second, just put here 1 second, 1 second, 4 second, 4 second, and then you can easily calculate the position and velocities. So now the sign of the position and also the sign of the velocity are very important. For example, here, for when the time is 1 second, the position is plus 10.1 meter. It means that you are talking about here, okay? So along the positive y direction. And if you have positive velocity value, positive sign here, it means that the particle is moving along the positive y direction. If you found minus velocity value, it means that the particle is moving along the negative y. Don't forget this ones, okay? Because velocity and acceleration and also position are vector. And for the vectors, positive and negative signs are very important because sign is showing us the direction of the vector. Okay, we have already discussed this one. So this is a free fall misconception. What I have told you that the last part of the question was this: the ball's acceleration when it is at the maximum height. What is the acceleration of the ball when it reaches to its maximum point? Acceleration is due to the gravity and it is constant everywhere. So acceleration here also given by minus 9.8 meter per square second. Okay, so it is discussed here. I will not go into detail. So now let me show you all these calculations within the graphs. This is the time axis, 1 second, 2 second, 3 second, 4 second, and this is the y-axis. This is the origin, roof level, 5 meter, 10 meter, and it goes. This is the maximum height of the particle when the time is 1.53 seconds, okay? So now we have positive numbers. The particle is moving upward from the origin to the y direction, and it reaches its maximum height, and then it goes back to the roof level, and then it goes down, -5, -10, -15, -20, okay, to the ground. This is the position of the ball as a function of time. And here you see the velocity of the particle as a function of time, 1 second, 2 second, 4 second, 5 second, again it goes. What do you see here? When the time is 0, the velocity is 15 meter per second. When the time is 0, the velocity is 15 meter per second, and it is positive. It means that the particle is moving along the positive y direction. So after some certain time, the velocity decreases, but again, it is positive number. It means that particle is still moving along the positive direction, but the velocity is decreasing. Look at the curve here. The slope of yt graph gives us the vy velocity. So what do you see here? That the slope is decreasing, then velocity is decreasing, but again, it is going along the positive y direction. Velocity is decreasing. At the beginning, it has 15 meter per second velocity, and then it is decreasing, decreasing, and finally at the maximum height, the velocity is 0, okay? But before the maximum height, we always have positive velocity because the direction of the velocity, the direction of the movement is along the positive y direction. Then the direction of the velocity will be negative, okay, after this maximum height. So now when the time is 1.53 seconds, the velocity is 0 because the particle is at rest temporarily for a second, for a moment, and then its velocity increases in negative direction, okay, because the particle is moving back. Do you have any question related to this up and down motion in free fall? This is very important. You may have such problems in the midterm exams and also in the final exam. Now let me finish with the velocity and position by integration. Don't be afraid with term integration. If you know very basic integral calculus, you can easily understand what I will discuss here. Now we will discuss the velocity and position by integration. So we will have non-constant velocity, and also we will have non-constant acceleration, like the acceleration of the car here. So when you are driving a car, let's consider that you are started from the rest and you are accelerated from rest to the 50 km per hour with some certain acceleration. And then from the 50 km per hour to the 100 km per hour, you have different acceleration, okay? So in order to calculate the final velocity of this car, you have to use this equation. What do you see here? Initial velocity of the car when the time is 0, integral from time is 0 to time t, acceleration, and dt. So what is the meaning of this? Acceleration changes as a function of time and all the accelerations for different times, okay? This is the integral. Or you would like to calculate final position of the car. this is equal to the initial position plus integral from the time is equal to 0 to the final time Vx dt. So this is the time integral of Vx. So this is the time axis from 0 to certain time, and here we have acceleration. What do you see here? Acceleration is not constant. In the previous transparencies, we have discussed the situations for the constant acceleration. But here, the acceleration changes as a function of time, okay? For the time 1, we have this acceleration. Here we have different acceleration. Here we have different acceleration. So we have such behavior for the acceleration. So what do you see here? Acceleration versus time. Here, let's consider that you have chosen very short time, then delta t here, and this is a. So a times delta t will give you the velocity, okay? Velocity here, velocity here, velocity here, velocity here. You have different velocities for each time interval. And in order to get the final velocity, you have to integrate this area, okay? We can divide the time interval between times t1 and t2 into many smaller sub-intervals. So the time is from t1 to t2, and we have many sub-time intervals shown by delta t. And from the average x acceleration, you know that it is given by delta Vx over delta t. Let me write it here. What was the definition of average x acceleration? Delta Vx over delta t, right? And if I take delta Vx, the change in the velocity, you will get this expression, a times delta t. So let's continue. In the limit that all the delta t's, very short sub-time intervals, become very small and they become very large in number. So you have many delta t's, many delta t's here. The value of average acceleration for the interval from any time t to time plus delta t approaches the instantaneous x acceleration at time t. So what was the instantaneous acceleration? Instantaneous acceleration was acceleration for a very short moment, okay? Let me draw this one. Here we have many time intervals, and this is the final time, t2. So just choose very short time here. For this time, delta t goes to 0. I'm talking about very short time. And here I have instantaneous acceleration for very short time. So I can consider that I have many instantaneous accelerations for different times, okay? So what I have here? I have here delta Vx. What was delta Vx? V2x minus V1x, final velocity minus initial velocity. So I can write it like this, integral from initial velocity to the final velocity. So what is dvx, which is given by a times dt? Velocity is given by acceleration times time, okay? So now I have limits here from initial velocity to the final velocity, but here I have limits from initial time to the final time because this is time integral. This is velocity integral and this is time integral. Okay, so I can write the velocity with this term, and then let's consider that you are calculating the total displacement. What was the displacement? So V average x, you know from the first lecture, delta x over delta t, right? What is delta x? x2 minus x1, okay? So here, just take delta x and which is given by integral from initial position to final position. And instead of dx, I can write v times dt. Vx times dt from the initial time to the final time. So if you solve this integral, then finally you will get these two expressions. Here I have x2 minus x1. Instead of x2, just choose x, and instead of x1, just choose x0. Final position, initial position when the time is 0, and we have this integral here from initial time when the time is 0 to the final time, Vx dt. So we have this relation for the position of a particle for non-constant acceleration, and you can do the same for this equation. So what do you see here? Final velocity minus initial velocity is equal to time integral of acceleration. Okay, instead of v2, just use vx. Instead of v1x, just use v0. Then final velocity is equal to initial velocity plus integral from initial time when the time is 0 to the final time when the time is t, and ax times dt. So we have two equations for the velocity and position if the acceleration is non-constant. If the acceleration is constant, you can use four equations which we have discussed at the beginning of this lecture. But if the acceleration is non-constant, then you have to use these equations for the position and velocity of the particle. I can give you one application example. As I have discussed at the beginning of my lecture, this has non-constant acceleration. So this fighting jet has non-constant acceleration. Okay, here in the Falcon Heavy, it also has non-constant acceleration. Okay, for this type of situations, you have to use equations for the velocity and position with constant acceleration. Sally, a lady, is driving along a straight highway in her 1965 Mustang at time t is equal to 0 when she is moving at 10 meters per second in the positive x direction. She passes a signpost at x is equal to 50 meters. Her acceleration as a function of time is ax is equal to 2 meters per square second minus 0.1 meter per cubic second times t. So look at the acceleration. In the previous questions, acceleration is just given with, let's say, 2 meters per square second. That's all, constant acceleration. But here, acceleration is given with an additional term, which is multiplied by time. So what do you see here? Just put time is 0, then this term will be 0. Just put here time 1, then acceleration will decrease. Just put time 2, acceleration will further decrease. So acceleration is not constant. It depends on the time, okay? Non-constant acceleration. So what is the question? Find her x velocity Vx and position as functions of time. Here we have acceleration as a time. The question is that just get a relation for the velocity as a function of time and get a relation for the position as a function of time. And the second part of the question, when is her x velocity is greatest? Maximum velocity of the Sally is asked. So what do you see here? When the time increases, 5 seconds, 10 seconds, something like this, acceleration will decrease. Finally, acceleration will be 0, and then it will go to negative because this negative part will be bigger for higher time values. Okay, so acceleration will be 0 for certain time because this will be equal to the first term, and acceleration will be 0, and after certain time the acceleration will be negative. Okay, then Sally will start to slowing down. So then the question asks, what is her x velocity? Another part of the question, what is the maximum x velocity? Last part of the question, where is the car when it reaches that maximum x velocity? So what do you see here? Velocity and position are asked. So we know how to calculate velocity and position for the non-constant acceleration. We have already learned this two equations. So you will use this velocity equation for non-constant acceleration, and you will use position equation for non-constant acceleration. So if you use these two equations within this question, you can easily solve your problem. So what was the first question? What is the x velocity and position as a function of time? So what do you see here? The question tells us that find her x velocity vx and position x as functions of time. So acceleration is given as a function of time, right? And here we have vx formula for non-constant acceleration. What is the initial velocity when the time is 0? It is given in the question, 10 meters per second. Put it there. Plus integral from 0 to t. Instead of ax, this ax is given within the question. Just take this ax and put it there. 2 meters per square second minus 0.1 meter per cubic second times t and dt. So what is the solution of this integral? The solution of this integral is given here. If you have such integral sign here, can you see the integral solution here? This one, t power n dt is equal to 1 over n plus 1 t power n plus 1. Can you see this one?
Yes.
Okay, then
Yes.
Good. Let me use the pen here and then try to solve. For example, let's consider that you have such integral. No, let me write down here. Let's consider you have this type of integral. The solution of this one, 1 over 1 plus 1 to t square. If you have this type of integral t square dt, the solution 1 over 3, okay, like this. It is given here, you see. So here I have acceleration, which is given in the question. If I take the integral of this one, I will get 2 times meter per square second times t, solution of this integral, minus 1/2 0.1 meter per cubic second times t square, solution of this integral. Then you can get the result for the velocity as a function of time. What was the question? Velocity as a function of time. Okay, so then we have the result for the velocity. What about the position? This was the initial position of the Sally, 50 meter, plus integral to t. So instead of vx, I use 10 meter per second and 2 meter per square second times t minus 1/2 0.1 meter per cubic second times t square. Instead of vx, I just use this one, and here I have dt, put dt, and if you take integral of this one, if you take integral of this one, if you take this integral of this one, finally we can find solution for the position as a function of time. Is it okay? Any question here? So with this one, I will finish and I will not go into detail, but here I have 3 graphs related to this example 2.9. Here, this is the time axis in second. This is the acceleration axis. Here we have time axis. This is the velocity axis. This is the time axis and position axis. So what do you see here? The acceleration here is at the beginning when the time is 0, acceleration is 2 meters per square second. Why? When the time is 0 here, we have this acceleration. And what about the sign of the acceleration? Positive. It means that it is along the positive, okay? So here we have 1 meter per square second after certain time, because acceleration is decreasing by time due to the negative term here on the right side. And finally, for certain time, when the time is 20 seconds, this second term here will be equal to the first term, and then acceleration will be 0 here. After this time, acceleration will be negative because here I have much bigger numbers of the time, and this term will be bigger than the first term. Then finally, we will have negative acceleration. You see, this is the acceleration versus time graph. And here we have velocity versus time graph. What do you see here? Velocity increases along the positive x direction, 10 meters per second, 20 meters per second, 30 meters per second, but the increase in the velocity decreases, okay? And this is the highest velocity of the car when the acceleration is 0. So after that time, acceleration is negative. It means that, let me show you here, that consider this is positive x, this is the origin, and here in this part for time is 20 seconds, we have velocity in this direction, and also we have acceleration in this direction. Before the 20 seconds, both acceleration and velocity are positive, and the car, Sally, is speeding up. After 20 seconds, again, the velocity is positive, but acceleration is negative after 20 seconds. So acceleration is in opposite direction. Then the velocity of Sally will decrease. So Sally will slow down. Okay, what do you see here? This is the velocity, and after 20 seconds, velocity goes down. Okay, but still in the positive x direction. Is it clear? Now yes. We have here, good. We have time versus position. What do you see here? Sally started from the origin here, and it is going in the positive x direction. So her position increases as a function of time, okay? But what do you see here? When the acceleration and velocity are in the same direction, it has upward curve here, and the curve in the xt graph gives us the positive acceleration, and after the 20 seconds, the xt graph has more or less negative curve, let's say like this. So remember the last lecture, in xt graphs, let me choose the laser pointer. In xt graphs, if you have upward curve, then it means that acceleration is positive. If you have downward curve, then it means that the acceleration is negative. So even from the xt curve, you can understand that here we have negative acceleration. Here we have a positive acceleration. Any question here? If you have any question, I can repeat that part. With this transparency, I have finished my lecture, and on Saturday at 11, we will have quiz from this chapter.